Welcome to the Strength of Materials 1 course. Today's topic of discussion is on type of stresses. This is a part of Unit 1 syllabus. So let us see the flow of the topic of our present discussion. As shown here in this picture, the discussion flows this way in the entire 15 minutes that we are going to spend. So in this particular discussion we are going to see how the concept of stress comes into being and what are the types of stresses, how basically the stress is classified, and what are the sub classifications in those primary classification, and what are some practical examples that relates to each of these types of stresses. So let's proceed. So specifically in this particular discussion we are going to see what are the reasons for the stress development in a material and stress definition, and some of the terms that are mostly similar to the stress term. We may get often confused with these terms, and the major classifications in the stresses, how basic classification of the stresses is done, and let's relate to some of the examples of the daily life in relation to the concept of stress. Now here is a question: why does the loads or external forces acts on a particular structural member? Is a very basic question. So we all know, as you can see here, you can take any structural member. For example, this column here. Why this column is subjected to loading here or external forces here? So it may be because of because of many reasons. Some of the reasons mentioned here. For example, it may be due to the contact with other members. The column here is subjected to load because it is in contact with the beam. Right? The load is coming from the beam onto the column. Right? Or you take a beam is in contact with the slab. From the slab, beam is taking some load. Or it may be due to the sulfate, its own gravity, its own weight also having some because of that also some external load is acting. And for example, this particular slab, it might have been constructed for some living purpose or some other official purpose. So as a result of that, there will be some kind of loads acting on that. So for when it is used for the whatever intended purpose for which it has been built up, because of that also loads will be acting. Or sometimes some kind of water tank or some other fluids are stored here. As a result also loads can also, or external forces may be acting any one of these structural members. Right? So these are the reasons why the loads or external forces acting on the structural members. After all, the structure is supposed to be taking some kind of loads, otherwise we don't build them, right? So now let's see, if you take a particular member, for example, here is a cylinder. You take a cylinder. On this cylinder, how many different ways the forces or external loads can act on this member. So this is a cylinder in unloaded position, not at all loaded, not being used at all, and you can later on you can apply any one of these forces. You can pull it away. Then that kind of force acting is tensile force or tension, and the compression force, it may be pushed in. You may pushed in, apply a force, it is pushed inwards. So then it is subjected to compression, or it may be subject to some kind of bending like this. Both ends you can bend like this. This is one type of loading, or it may be it can be applied forces like by applying a shearing force, such as cut off these two parts. Then the object is of cylinder is subjected to shear force, or it may be subjected to some twisting movement or torsion such as this, or you may apply any one of these combinations. As you are seeing here, any one of these combinations might be acting in a particular cylinder. Now the question is, our present discussion is, how does the material of the cylinder respond to the external force application? What happens inside the material? That's what we are interested in. Right? When you apply this external force, maybe any one of this form, maybe a tension force or a compression force or a bending force or a shear or torsion, or a combined loading, any one of these forces or external loads may be acting on this cylinder, then what happens to the material inside the cylinder? Right? That's an interesting way to think. So what happens if this is a material? Generally the solids, particularly in strength of materials 1, 2, all these courses, in our general structural problems, we deal with the deformable bodies, not the rigid bodies. We deal with the deformable bodies. So in case of deformable bodies, when you apply some external forces like this, and because of that external force, what happening inside the molecules, inside the material, right? If you apply a force, automatically the immediate thing that can happen is, in case of deformable bodies, the body starts deforming. The elements in the material, or the particles, they starts deform because of the external force. Now inside, because there is attractive forces between the particles, they get disturbed by this external force, but they want to maintain that equilibrium. The attractive forces, what they will do is, they will not they try to stop this particular deformations caused because of the external force. In the process, right, this opposition force is what is we are referring as stress, right? So the internal resistance that builds or sets up within the body to balance the effect of the external forces, that is what we are calling as stress, right? So here mainly just 2 points. We can, same thing when you apply tensile force like this, when you apply compressive forces, you can see this is how the opposing force acting inside the molecules. So the intermolecular attractive forces which are already available between the particles, they will try to oppose the deformation that are caused by the external force application. In this process of offering resistance, the molecules are offering this resistance because they are already attractive forces. The attractive forces are getting weakening because of the external force, because the deformations takes place. They will try to stop. In the process, the stress builds up in the material. Okay, that's what we are referring as stress. Right. Next. So once you understand the concept of the stress, basically, one more time, the concept of the stress, how it develops because of the internal resistance that builds up in the body because of the external force application, right? what that external force does? They try to deform the body, and to balance the effect of that external forces, the intermolecular attractive forces will oppose that deformation, right? So that deformation, that opposing forces offered by the molecules inside is what we are calling as stress, right? Now, how is the stress different from some? Often you will be using a similar time. Sometimes in place of force, you will be using stress. Like that, there are some analogous terms, similar terms related to stress. Sometimes we'll be using force, sometimes we'll be using stress. But there is a difference because both are forces in one sense. Stress is also force, of course, you say for unit area, right? So let's see the primary difference between stress and force. The force in external pull, right, or push, you can say, pull or push, that changes the equilibrium of the body. Whereas this stress is an internal resistance experienced or developed by the material, right? Now I am defining stress is an internal resistant force developed by the material in response to the externally applied forces. In other words, external force applied forces are not there, there is no question of development of the stress, right? So differentiating here, force is external pull or push that changes the equilibrium of the body, whereas stress is an internal resistant force developed by the material, right? We already discussed how it develops. Also we discussed, right? The intermolecular attractive forces, they try to oppose the effect of the force, right? So in response to the external applied force, that's what is stress, right? Another way of differentiation is it opposes the deformation cause, whereas the force causes the deformation, but this stress, it opposes the deformation caused by the external force. Now another similar term is pressure. Is pressure and stress both are same, right? Is it same? You can see here is a cylinder. On this cylinder, there is a fluid pressure acting. Inside there is a fluid or some kind of water, gas, whatever it may be. Any fluid is acting inside the cylinder. Now here we can see the difference between pressure and stress. So the fluid exerts some pressure. That means what? It is an externally applied. The external force per unit, both are actually, pressure is also, we say force per unit area. Stress is also force per unit area. But there is a difference. The difference is that the external force per unit area is what we will call pressure, but the stress is internal force. It is you cannot see that, right? Stress you cannot see. Stress is an internal force of resistance per unit area experienced by the material, whereas acting on the material, the first one, this is an experience by the material due to the applied load, right? From the externally applied load, this develops, right? Internally it develops. It is actually a resistive force. So the internal force of resistance per unit area experienced by the material is called stress, whereas the external force per unit area acting on the material is what is called pressure. Another questions that are bothering is a stress geometric property or material property like that. Stress is neither a geometric or material property. Another one is a stress a vector or scalar? Actually, stress can act simultaneously in two directions or even three directions. So it is neither a scalar nor a vector but a tensor. For those who don't have idea about the tensor, is we can say scalar and vector both are a subset of these tensors. And now another question that will be arising in our minds is stress and strength. Sometimes we'll be using in our terminology. Is stress and strength both are same? When we say why the material fails, we say that the material strength is has been already crossed, or the material is subject to more stress than the strength of the material. Like that we'll be using interchangeably. So is there any difference between the stress and strength? Yeah, there is a difference. Stress is a measure of amount of force an object experiences per unit area, right? Whereas strength is a material ability to withstand how much stress that material can withstand. That what we are calling as strength. Whereas stress is a measure of amount of the force an object per unit area, right? Now let's see how to measure the stress. How the stress is measured, right? So let us say take a small rectangular element here subjected to some external force. Now I will cut off at some location, say xx. There is I used a cut a section xx at some point at any distance, say at x distance, either from left or right. You can cut off. Now examine what happening is the at every cross section the bar or rectangular bar we are taking is in equilibrium under the action of the force P, right? Now at this section xx we say, right, if you want to define stress or measure stress, how the stress is defined as the force intensity, right, or force per unit area, force per unit area or force intensity at this location. This is what we are calling as stress. At any cross section, the force per unit area is what is called stress. That's how we can calculate. Right? You take the cross section where it is at any cross section that you are taking, right? That force divided by the cross sectional area is that's how we can calculate the stress. Of course, we are making an assumption here. What is the assumption? The assumption is that the stress is acting uniformly. Is it true always? May not be. For example, you may have some kind of force somewhere or some weakest material parts. In that case, no, it may not be same. Provided that we assume that it is having same cross sectional area and uniform properties of the material. Yes, it may be uniform, the stress intensity. So that's what we are assuming there. Over the entire cross section, the uniform distribution of the force is acting. If at all, there are problems where the stress intensity is not identical or uniform. In those cases, those problems are called, say, stress subjected to some particular area, may be subjected to stress concentrations. Now the units are, because we are saying force per unit area, it may be stress can be expressed in Newton, right, per meter square, or Newton per centimeter square, or Newton per mm square. Anyway, right, when we are dealing with the problems, these are the terms that we will be mostly using, like megapascal, gigapascal, kilopascals. We all know kilopascal is 10 to the power 3 and giga 10 power 9 and megapascal 10 power 6. And interestingly, most of the times we'll be using this term megapascal, 10 to the power 6. You can simply say 1 megapascal equal Newton per mm square. This may be very useful while doing conversion, unit making conversion. Mostly we'll be using Newton per mm square, and we'll be examiner also maybe while solving problems, we may be giving in megapascals. You can simply, wherever megapascal comes, you can simply write Newton per mm square. Now, as come to the core of our topic, how many types of stresses are there? Basically speaking, there are only two types. One is the normal stress, another one is the shear stress, right? So why that name normal stress come, that we will see. It is called shear stress, and some other names are also there for this. For example, normal stress has many names like longitudinal stress or direct stress, right? All these names are there. Similarly, for shear stress, it may be tangential stress. You may be using that term, that kind of terminology, shear stress or tangential stress. So let's see why this normal stresses came. What is this normal stress? Suppose you take a particular rectangular bar, you apply some force here, or you can apply some stress. Then that particular stress, why it is called normal stress? right? So if this is the cross sectional area, so in other words, the stress we are representing in terms of the its orientation towards the cross sectional area. If this is the cross sectional area and your stress direction is perpendicular to this or normal to this particular cross section, then we will say it is a normal stress. Right? So if the stresses are normal to the areas concerned, whatever area we are be taking, let's say this is the area, and the stress is normal to or perpendicular to this particular uh, cross sectional area, then we will say it is called normal stress. Same thing here, compressive stress is acting, here is the tensile stress acting. So depending upon whether they are pulling or pushing, we may say normal stress, tensile or compressive, right? Either acting out of the area or into the area, right? So normal stress is you can say subdivided into tensile and compressive stresses. Here is an example. You can find many examples. Here is one example. There is a bridge, a cable stayed bridge, where there are some vehicles moving on here. Because of the vehicles, the top portion of the deck is subjected to the compression force or compressive stress, whereas the ropes here, cables, you can say, they are pulled like this because of the loading. They are subjected to tensile forces. Okay, so the type of stress is normal stress here. It may be tensile or sometimes maybe compressive. Now, within the normal stress, in the sense when you are considering the stress normal to the areas concerned, it may be acting in one direction or it may be acting, like in this case, one direction, right? Or it may be acting in two directions, such as this sigma 1 and sigma 2, x and y direction basically, or it may be acting in three directions, x, y and z. Depending on the directions in which they are acting, you can say the normal stress may be uniaxial normal stress, biaxial stress, biaxial normal stress or triaxial stresses. Okay, depending on how many directions it is acting. And this is more common, either biaxial or uniaxial. Very rarely will, most of the examples, practical examples will be on biaxial or triaxial state of stress. Now, bearing stress is also a form of compressive stress. Bearing stress is not a different type of stress. Is when the one object, let's say there is a object, there is a soil here. This object is trying to press the soil here. Now that stress at this surface, right, the contact surface, we will say the bearing stress is acting. So basically, when two objects are pressed against each other, then at the interface there will be a bearing stress, right? This is a form of normal stress only. Now, often you will be used also hearing the terms like bending stress and torsional stress, right? What are these stresses? Particularly bending stress is also a form of a normal stress, because this bending, what it does is, suppose I am having a simply supported beam, apply some load at the center, then the beam bends this fashion, the top part of the beam is under compression, the bottom portion of the beam is under tension. So on the top there will be compressive stresses on every element, whereas on the bottom you will be having a tensile stresses. Okay. Now there is a twisting moment. This comes under shear. Let us see what is shear stress, and we are going to discuss. So when you apply a twisting, this is also not a different type of stress. Basically it is a shear stress. We will see how it is shear stress, right? Twisting moment also develops shear stress. So let's see the second. We already come across shear stress terms, because in the classification so we told already normal and shear stresses. Normal stress we define. Now shear, how does this name, or tangential stress, how this name came, is just opposite to the previous direction. If the cross sectional area of the block is subjected to forces or distribution of the forces which are parallel, in the previous it is normal, now it is parallel to the areas concerned. In other words, if the forces are acting in a direction tangential or parallel to the areas under concern, right? Then we will say it is a tangential or shear stresses. Here you can see the forces are acting parallel to the cross sectional area, which is considered this particular area. Then shear stresses. Often this kind of shear stresses, leads to shearing of the body. It departs the body into pieces. Here is many such examples we can relate in daily life. Cutting of the vegetables, you can see here. The you take a vegetable and press with a knife. The shear force will be acting mutually opposite direction on both faces of the vegetable, and then it will be cut off into the pieces. Same thing cutting a bread here. Pieces are teared off because the shear force is acting mutually opposite direction on this. Similarly, cutting a log of wood and so on. Many such examples you can see. Painting on the wall, right, or the brushing the teeth, right, uh, and turning of a screw of a tap. So many examples. All these are what basically what we are doing is we are applying a force tangential to the cross sectional area under concern. Similarly, our walking on a surface or ground, that also force is acting in a parallel to the floor. So all these examples comes under the application of the shear force or shear stresses. And here is an important point. Finally, when you express or when you represent stress, the at any point the stress is basically resolved into two directions. One is parallel to the area concerned and perpendicular to the area concerned. Just now we told the parallel to the, if a stress is acting parallel to the area concerned called shear stress and normal to the area concerned called normal stress. So at any space, if you express any stress component, usually it is represented in two directions. One is in a direction parallel to the cross sectional area, another one is perpendicular to the cross sectional area concerned, right? Now another example of the shear is what you call a bolt, right, in a lap joint, and when two pieces are connected, bolt or rivet you can say, and they are pulled apart, the particular rivet or bolt is subjected to single shear in this case, whereas here because it has been joined through two different plates, it may be subject to double shear. So finally, let's connect the things that we have seen in the original picture. What all we have been discussing is the development of the stress is because of the application of the external forces. What the external force does, they will cause deformation, and thus deformation is opposed by the intermolecular forces in the material. In the process, the stress develops, and the stress has been classified into mainly two types, namely normal stress and shear stress. The normal stress is nothing but a stress acting in a direction perpendicular or normal to the concerned area, whereas when it is parallel to the cross section area, we say shear stress. And this particular normal stress may be acting in one direction, two directions, or three directions. Based on that, we may be giving uniaxial, biaxial, triaxial state of stress. Whereas other forms of stresses like bending stress is also a form of a normal stress having combination of tensile and compressive stresses. Whereas torsion stress is another example of another form of shear stress, right? And we can see several examples. Shear stress, many examples like cutting vegetables, cutting a log of wood, walking on the road. All these are examples. Now many examples on even hanging weights. All these forces acting on the car. This comes under normal stresses. So that's all on the topic of the normal stresses. Now there are some questions for you to reflect, so you can see that. So that's all about the topic of the uh, types of stresses, and if you have any questions you can post. Thank you.